Good afternoon. My name is Chandra Singh, and I am applied researcher in agriculture engineering and technology at Lethbridge College. Today, I'm going to cover some basics about automated in-bin aeration of canola. This is the brief overview of my presentation today. It includes canola production, canola spoilage issues, safe canola storage methods, automated in-bin aeration, and summary. Canada is the largest producer of canola with 20 million tons of annual production. Canola industry contributes almost nearly $30 billion to Canada's economy. 90% of canola is exported. Saskatchewan, Alberta, and Manitoba account for 54.5, 28.3, and 16.4% of production, respectively. Despite such huge contribution and production of canola in Western Canada, prairie farmers face adverse weather challenges during production and storage almost every year. In 2019, it was one of the most difficult harvest season, and as you can see in some of these stories, that was called Harvest from the Hill that year. This is a screen capture from November 29 crop report, and in that year, as of November 5th, 17% canola crop was unharvested in Alberta. So this shows you the challenges in certain year despite having a very good crop. High moisture, temperatures, green seeds, dockers encourage respiration. And heat from respiration of grain generates additional moisture and that leads to the mold's growth, which may further be a cause for development of hot spot due to the self-heating. Spoilage results in weight loss, quality, nutrition, and seed viability losses. Molds in the grain may produce carcinogenic mycotoxins. This is an example from this is a story from 2016 in Saskatchewan when a canola bean caught fire. Though the exact cause of this fire is not known, but most likely it started with the self-heating of canola. Though the bin did not have any cables. This is another bin that had actually the cable, and as you can see here that canola was harvested at 26 degrees Celsius. It was dry seed, but within 8 days, the canola temperature increased to 30 degrees Celsius. And next 4 days, it increased to 40 degrees Celsius. So you can see how fast the temperature can go up if the bin is not aerated. So what they did in this bin, that they actually moved the canola out of the bin, and while doing that, the canola got cooled, and then it stayed for the winter period, and they sold in June following year it's as number one grade with no damage, 8.4% moisture content. So you can see without monitoring, this whole bin could have been deteriorated. Seed moisture and temperature are the two most significant parameters that determine safe storage life of grain. Dry and cool grain is the bottom line for a safe storage of not just canola but any grain. In bin aeration is the most common and low cost cooling method. efficient drying, aeration, and aeration are critical for long-term safe storage of canola. This is a chart that tells you uh, uh, at the how long you can store the seed at given combination of grain temperature and moisture. So as you can see here, uh, if your canola is below 10% moisture content and it's cooled down to 5 degrees Celsius or below, then you can safely store up to 1 year. Uh, it is recommended to cool it to 2 to 5 degrees Celsius and then store it in that condition for up to 1 year. Aeration is the process of controlling the seed temperature by cooling it. In general, canola harvested high moisture and high temperature despise, so it's important to cool it. Aeration reduces the heat and moisture of respiration, thus arrest the growth of malt. Crop can be stored for longer duration if properly aerated. Aeration also helps in moisture migration due to temperature gradients. Aeration is not unknown to any farmer. Most of them have been practicing it for for uh, many years. In recent years, there have been some contradicting claims about the aeration, as you can see this farm media headline. So it is important to understand how the aeration works and what is the best way to manage the crop by properly aerating it. For efficient in-bin aeration, it is important to have in-bin temperature and moisture monitoring cables, sufficient airflow in the grain bin for uniform cooling, and automated aeration control rather than manually operating the fan. And also have the closed loop control system with temperature input from the seeds. This is a smart grain management system which has both temperature and moisture cables. It has a local weather station. Also, it has plenum pressure and temperature sensors that is used in fan control. These are the airflow requirements for different grain conditioning operations. Aeration has relatively airflow rate required as because cooling is much faster than drying. So zero point 0.1 to 0.25 CFM per bushel is required. However, canola is a small seed, so it has high resistance to airflow rate. So it's not easy to get the desired airflow rate, particularly large and taller beans. So proper aeration fan should be selected. This chart shows here the in a 40 this chart shows here in a 48-foot diameter bin the airflow rate at different uh, grain depths by different type of fans. That includes 10 horsepower axial, 20 horsepower low speed, high speed centrifugal fans, and 30 horsepower low speed, high speed centrifugal fan. So as you can see, when you increase the grain depth, airflow is significantly reduced. So if you're using a tall bin for aeration or storing grain, then it is recommended that you should go with the high speed centrifugal fans, as you can see here. So it is efficient to uh, use automated fan control for aeration for several reasons. And one of them is uses the cooling potential of ambient air. So it's only operating the fan when the air is cooler. It's not running 24-hour where you might be cooling in one time window, but then you might be reintroducing the heat, and then it will probably not just warm the grain, but it might also cause some of the condensation in certain areas of the bean. It operates the fan when ambient air is cooler than the actual grain temperature. So that's what I mentioned about the closed loop system. That means that it tracks the control system, tracks the actual grain temperature and the actual uh, ambient conditions, and then makes the decision based on those conditions. It also minimizes the overtrying by operating the fan in selected EMC band. So the fan operation is done only when air is in that specified band. So you're not overtrying or rehydrating the grain. Also, it automatically stops the fan below freezing temperature, particularly in the cooler nights, because operating the fan below freezing temperature may actually freeze your vents, and which will further reduce the airflow inside and its excessive use of energy. And there is no benefit of cooling the grain below 0 degrees Celsius. Is also considered the fan warming due to static pressure. So if you have a plenum sensors, that actually measures the actual plenum temperature. And due to this static pressure, it adds 1 to 2 degrees Celsius heat rise. So it is important to make sure that your plenum temperature is below at least 1 to 2 degrees Celsius below the actual grain temperature to make sure there is enough temperature gradient to provide cooling. Otherwise, you are operating the fan without any cooling effect, and that's excessive or use of energy or waste of energy from the fan operation. It's also important to have a local weather station, and that's an input to the fan to make sure that the fan date decision is based based on the real-time local weather conditions. This is an example of an automated aeration control system. As you can see on your right, there's a weather station, this white piece here on the fence, and that's connected to this another node, and that's the top portion of the blue, and that communicates with the gateway. On the left side, you can see in the grain bin on the top, there is a cable node that takes the data, moisture temperature data from the bin from different cables, and then communicates wirelessly with the gateway. And gateways is also connected to the fan control node attached to the grain bin for the fan operation. And from the gateway, all the data is thrown to the cloud, and from cloud you can access the data and control the fan and manage the grain bin. Once you make a decision or turn on or off a fan using your from the cloud based operation, then it communicates that decision to the fan node. And based on this actual fan control system, that the decision is made based on your target grain type, grain condition, and that's the most effective way of ensuring that efficient cooling. This is my summary. Uh, Canola has high risk of spoilage related to other grains due to its high oil content. Self-heating can occur even in dry canola, partially because of the nature of the grain itself, or it's possible that though the grain is dry, but there could be a small patch with high moisture content that can initiate the self-heating, and then that can spread to the whole bin. Storage bin should have temperature and moisture monitoring cables. I showed in one of my slides that how it helped them monitor the increase in temperature and use some corrective actions by unloading, cooling it, and putting that back to the bin. Other bins showed potentially that caught fire because it did not have any temperature monitoring attached to the cables. So it is important to have the monitoring cables in every canola bin. Bins should have sufficient airflow for aeration, If there's not enough aeration and uniform aeration, then maybe certain area, even you are operating the fan, but one certain area, particularly the peak cone, that area, core area may not have enough aeration to cool, and then can still uh, start self heating in that area. And that could be significantly spoiling the grain. Energy efficient and uniform aeration can be achieved with automated fan control. It's a real time decision based on the grain conditions and ambient condition and your target. And that way you can minimize the risk and also save excessive energy uses for the fan. I would like to thank all the funding partners for my programs in post-harvest technology at the Lethbridge College for their supports. Thank you.